Okay, guys, let's get started with the uh, final basic neural network architecture module, which is transformers, right? Uh, let's get to know what is transformers, and before that, let's start with what we have finished with the existing technologies, right? So the technologies that were developed before the transformers, right? Because transformers were not born in a vacuum, so it was developed uh, inspired by several other technologies that were developed. Uh, that means most of the neural network architectures that were developed up to now, like the RNN modules, like LSTMs and their attention models, basically, right? And also inspired by the multiple filter concept that was used in convolutional neural network architecture, right? So this is, we can say this transform model was developed based on the concepts that were developed using the attention models of RNN modules, and also the filter uh, like a scaling with filters pattern that is used in convolutional neural networks, right? So those two are used together, and but the transformers are somewhat different from all these together, but it is very novel and it is bit complex, more than either convolutional neural networks and LSTMs and GRUs. But it is revolutionary because the concept that it is uh, proposing and it is demonstrating is somewhat different. That means it is novel. That is why it was very successful. And let's see what are the drawbacks that were there in the earlier recurrent neural network model, so that you can see how what the transformer is trying to address with its new architecture, right? So let's see what are the limitations of RNN models at first. So here what we are going to discuss is about the deep sequence models, right? So we have in the deep sequence models, uh, we discuss about RNNs, GRUs, and LSTMs. There we have let me draw it like this. So we have, for example, if it is a RNN or LSTM, so we are not drawing it separately for RNNs, GRUs, and LSTMs because most of them work the same, right? So in RNNs and GRUs, there's one hidden input. In RNNs, it is known as hidden input. In GRUs, it is known as cell state, right? In LSTMs, there are two inputs. One is cell state, and the other one is the hidden state, or the activation of the previous time step, right? So there are two time steps for LSTMs and one for uh, GRUs and LSTMs. Sorry, GRUs and RNNs, right? Uh, so for the simplicity, let's think about RNA so that we can draw much complex stuff without drawing two arrows, right? So, and here we discussed, so we can, when it comes to LSTM, so in the RNNs, right? So we can have uh, RNNs into both directions, right? And combine their inputs as outputs, right? And the inputs also we can give as different combined inputs for both directions. So those are known as, so those are the inputs, right? These are the outputs. So those are known as bidirectional LSTM, bidirectional RNNs, right? So once these outputs are given to, say, like, so what I'm trying to do is I'm trying to explain what I'm like reminding you what we learn about sequence models, right? And continue with what we have learned. So then we suppose we have another, and there we have, sorry, we have another sequence of RNNs, which is a unidirectional RNN. So that means these are bidirectional. This is a unidirectional one. For each RNN, so there's an input, and this input is getting attention. That means they are weighted with the attention of these, of each of these inputs, right? That's all. We getting weighted with the attention of these outputs, right? Outputs of these bidirectional RNNs, right? So that is how the attention model of the RNNs work, right? So this one, this sequence is giving the output like a one output, or it can be a sequence of outputs like this, right? So this sequence is what is going to give you the output from the attention model. So these are bidirectional LSTMs, which are also given the inputs like same as these inputs, but these bidirectional RNNs will provide the attention that is required for weighting each of these inputs into this sequence model, right? So if it is a RNN, it's RNN, right? If it is LSTM, it may be LSTMs with two hidden states, right? One for the cell state, another as the normal hidden state or the hidden state, right? So now you can remember, right? So this is what we have learned about uh, attention models, right? So now let's keep this in mind, and let's see what are the problems with these models. So before going into the attention models, what are the general limitations of RNN models? The first thing is that when there is a long num long sequence model, like say like 100 or thousands of time steps, then training these RNN models, RNN time step, are very difficult, right? So because you have to backpropagate, do the backpropagation through time, right? If you can remember, right? So outputs are used like this. So these hidden states are backpropagated through the time for finding the uh, for training this sequence model, right? So when there are 100 or 200 time steps, then you have this backpropagation has to happen in 200 uh, layers. It's not actually layers, but 200 steps, right? So which is very inefficient. So you can't, because these are similar to the layers of an ordinary neural network. Uh, so we know, right? These layers cannot be made parallel, right? So that means you can process or do the computations of a single layer in feed forward neural networks. You know it, right? So if you have uh, two two dense layers to feed forward neural networks like this, right? You can do the computations. Okay, all the three are connected to all the three, right? So when this kind of feed forward network is there, in order to do the back propagation or the forward propagation, calculations can be done with matrix and vector calculations, right? Accelerated by the hardware of the computer. But when it comes to when you are backpropagating from one layer, from this layer to the previous layer, it cannot. These two layers cannot be uh, trained in parallel, right? So that means first you have to wait until these gradients are calculated for this layer until you move into the previous layer. Because of that, you can't do the calculations in parallel when it comes to moving from one layer to the other. So because there are many layers in the RNN model, you can't uh, do this backpropagation and the forward propagation steps in parallel. So that would take a lot of time to move from this node to this node and this node and so on, which is sequential, right? So this is because of that, those are very slow, right? That is a very big problem with this sequence model, right? And the other problem that we know well is that when there are too many layers in the neural network, what happens is there are some problems occurring, like the vanishing gradient problem and the exploding gradient problem, right? That means we have learned this, right? So when we are moving uh, from here to here, the gradients are getting diminished, and so in the later stages, these modules will not learn that much because the gradient is almost zero. So that is vanishing gradient problem, right? And so in some cases, the gradients that are propagating in this direction are getting exponentially more and more. So the gradients will get increased into a very large number. So we should overflow uh, digital the available memory size for a particular integer or a long number, and this should provide an error, right? So that is the exploding gradient problem. So we have learned about some of the solutions that we can do, but still, when there are many number of time steps, that becomes a problem, right? And the other problem is that suppose when you are moving information from one time step to the other, all this information is encoded in this vector, right? In the hidden state. So in the RNN, there's only one hidden state in RNNs and GRU. So in LSTMs, there are two types of hidden state. From here to here also, there's a one hidden state. Right? From here to here also, another hidden state. Right? So when we are moving from one time step to the other, all the information of the history should be represented in this vector, right? Whatever the number of time steps that we have passed, when we are moving from one time step to the other, all the historical information are encoded in this vector. Because this vector is limited in size, because we can't have very large vectors because of the problems with the backpropagation and so on. We can't have a very large vector. Because of that, this vector becomes a bottleneck for keeping the historical information. Right? That is also a very big problem when it comes to uh, RNN model, RNNs, LSTMs, and GRU modules, right? Because these vectors have a limited amount of capacity to keep information. That is the other problem. So, and the other common thing that we have learned is that when it comes to uh, mainly the RNNs, the historical information gets forgotten quickly due to its nature. In GRUs and LSTMs, we have implemented certain functions, mathematical certain ways to avoid them getting deleted unless a specific condition is met. But still, when we are having a very long sequence of time steps, then the historical information can get forgotten. Say like thousands and uh, 10,000s or millions of timestamps. It is not possible to propagate the information from one time from the beginning to the end, because things are getting forgotten even in the LSTMs and GRUs. Right, so that is another problem with scaling the length of these sequence models when it comes to the current architecture that we have learned about RNNs, GRUs, and LSTMs. So what we have learned in the previous slide is about this one is related to attention models, right? So you have learned it, right? So, so later in 2014 and 2016, uh, some researchers have found that uh, because we were having a lot of uh, giving a lot of weight, or the having a lot of memory consumption and the processing in keeping the information from this state to the other state, keep moving them from one state to the other state, uh, is expensive. That may not be the thing that we have to focus, right? That means what they have found was, like we have learned in these attention models for the RNNs, where these attention models were significantly better than the earlier models. That means compared to these previous sequence models, these attention models were significantly better. So what they have found was, uh, if we have only the attention, that is still very good, even when there's no sequence. This so that means sequential information is preserved. So, for example, suppose now we have these. Suppose these are bidirectional LSTMs, right? In two directions. So this information is provided to give the attention to another set of sequence, right? So that, like we have learned. So what they have found was that this sequence is not that important. So what is important is giving the attention to each of these inputs, right? So that means the order of the inputs is not that much important, or propagating information like this from one time step to the other is not that important, right? So the problem we had with the previous models with these limitations was that propagating information from one time step to the other, right? So because keeping moving from here to here to here, it takes time, and it takes it's very computationally expensive to do the propagation and so on. But because now we only want to have the attention, that means if we can have only the attention but not the sequential stuff like this, if the as they have found that the models are working better in these cases, means when there's even when there's no sequential information but only the attention, the models are working really well. So what they have found was they were proposing a new architecture which is not based on these sequential models like RNNs, GRUs, and LSTMs. They have proposed a new model known as transformer model, right? So in 2017, they have published this paper known as "Attention is All You Need." That means this attention is what is given the priority in this new architecture, but not the sequential order of these tokens. However, right? So in the bag of words example, if you have learned about in the text analytics or somewhere, we know, right? So when we break a sentence or something into a sequence of words into a bag of words by breaking them and ignoring its sequential information, it loses a lot of information, right? So that means if you want to have the full potential of the model, you should have the sequence of these times, these inputs as well, right? So for example, if we are giving x1 in the first time step, second time step x2 and x3 and so on. So we have to make sure that we encode that the x1 has come before the x2 and x2 has come before the x3 and so on, right? That is the sequence of these inputs, right? Unless you specify it, this sequential information will not get given to this new transform model, which is not, this is not a transform model, right? So this is an old attention based RNN model. So suppose we have this, suppose there are some new transform model which is different from these models, and in the transform models we don't directly do this kind of web propagation, but we just consider these x1, x2, x3 as just some inputs which has no order. But later what they do is we encode these vectors, right? So we add some information into these vectors about the position of these inputs. For example, if you take this x1 input as a vector, and then we add some information into this vector saying that this is the first index. We get this vector and then we encode with some information. This is the second input, third input, and so on, right? So let's see how it is done in the attention in this transform model. So this position information is only added into these vectors, and but they are not. So we don't have to do this step by step, time stepwise back propagation and the forward propagation. We are just taking them as inputs, and we can process all these inputs, all these x values at the same time. So there would be no problem of having parallel computations, because now we have all these inputs. Now we can do the processing in parallel, right? So that is the main advantage of transformers, and not only doing these things in parallel, right? So in convolutional neural networks or the feed forward networks also would do this thing, right? Like doing the computations in parallel for all the inputs. But the difference is that we are giving attention for each of these inputs. So before we do the computation, so we have a model called self attention first. That means we are maintaining a weight matrix where we are giving the attention for uh, attention against each of these inputs, something like this matrix, like x1, x2, x3. So this is x1, right? x1, and a matrix against their own values, x2, x3, and so on. So when we have this matrix, we can maintain there's so then this is a 3 by 3 matrix. You can have the vector weight values for each of these inputs, right? Where you can do the where you can apply these weight values directly to each of these inputs. That means you can multiply these weight values directly with the input values, so that you can do the processing very fast, right? So once you have given the attention, then you can go to the next step, and then we have a feed forward layer, and this is known as uh, the basic component of a transform. Right? So this is the very basic way of explaining a transform. So this is the actual transformer model architecture that was proposed by the paper, which I specified earlier, which is known as the attention is all you need. Right? So this is the uh, transformer architecture. So these blue uh, partitions were not given in the paper, but I have drawn this to make you understand easier, right? So this blue section is known as the encoder, and this one is known as the decoder, right? So there are two encoders and decoders where you might have learned, right? So in these RNN models also, we can have encoders and decoders. For example, if you want to do some machine translation, that means if you want to translate from English to German, right? So we give each of the words to each of these inputs into the sequence model, into the into say for LSTMs, right? So say now this is without any attention for the simplicity, right? So we give some inputs like I like cats, something, right? So what happens is this information will get encoded into this vector, into a vector, and this encoded vector can be decoded by another uh, sequence of LSTMs, something like say it is a uh, English to Sinhala translator, right? So the first output would be if it is a English to Sinhala translator, because I don't know German, so I will explain it in Sinhala, right? So it may be like I like cats. It would be translated to like mama or mama asai. Sorry for my handwriting. I haven't. This I am using my non-familiar hand. Mm, who's on? Sorry, so my handwriting is very unclear. Right. So when you are given this output, it is given back into the as the out input for the second time step. So this is how we are generating. So this output is given as the input for the third time step, and so right. This is how this kind of how this encoded vector. So this one is known as the encoder, and this part is known as the decoder. Right. So this is how actually the machine translation happens. First, you encode your that is how it was done with LSTMs and GRUs, right? In commercial systems as well, like Google. Say here you encode this information or the sentence into a vector or some numerical information that then that vector is then decoded into the other language with the sequence model, right? So this one is analogous to this transform model. So in this transform model, instead of this encoder, we have this encoder, right? Instead of this decoder, we have this decoder. So we are going to learn how each of the component of this encoder and the decoder works, right? Before we moving into that, let's try to simply go through what are there in this encoder and decoder, right? So what it is, this is something like this. So it gives some input, something like this, I like cats, right? So now it is input embedding, right? Uh, we have learned about word embeddings, right? So what we do is, so because these words cannot be encoded, in here also we use embeddings, right? So although I haven't drawn, for LSTMs also we use embeddings, and the output is also given as vectors, and those vectors are then used with the softmax layers to generate these singular words, right? So I haven't drawn it, but all those things should be there when it comes to machine translation, right? So here I haven't specified it, but here we know this in the architecture itself, it has specified this. These are the inputs uh, like words or something. So that is encoded with the embedding, like word embedding, like word to it. But in transform model, all word embeddings like word to egg and glow are not used. There's a specific type of embedding used, which is known as, as I remember, word-based embedding, I guess. Uh, we don't have to learn that much, but if you are interested, then you can search and see how these word-based embeddings are working. So that is not really with using an existing word embedding like word to egg, but you can calculate the this word piece. You can find the word pieces. That means instead of using individual words completely, you can break the words into several pieces. Like, for example, cats. It may be the word in word piece embedding. It may be cat may be considered as one piece, and the s can be considered as another word, right? So that would be automatically generated with word piece embedding. So we don't have to think that much, right? So it would be automatically converted into this input embedding layer, right? So each of the words or the word pieces will be converted into a set of vectors, and these vectors are then encoded with this positional encoder, right? So what this positional encoding does is same as what I have mentioned earlier, where I am encoding saying that I is the first index, like is the second index, cats is the third index. So with these, so these are the positions, right? These are the positions of these terms. So here what we are doing is we are encoding these positions into another vector, right? So these positional encoding vectors are then added to this word embedding vector, right? So, and those two are added, and then it is moved into this section, right? In this section, what it does is it would have three inputs. One is known as key, this is known as value, this is known as query. So to simplify it, we use the letters K, V, and Q, right? For this section is known as multi-head attention, which is the most important concept that we learn with transformer model. So I will explain it later, right? So in transformer model, in multi-head attention or even in the single head attention, we should have two inputs. One is the key, and one is the value, and one is the query, right? There are two equal sized uh, vectors, right? That which we need for this block. So I will explain what this block does. And then what happens is this input is used to add and norm. So add means we are using this input as a residual connection. So if you have learned about this ResNet architecture, which is used in convolutional neural networks, there we have explained how this ResNet or the rest in the ResNet, how these residual connections or these bypass connections are uh, improving a deep neural network. Right? Say like when this suppose this multi-head attention has learned to output a very low output or something like 0 or something for all the values. So now then this residual connection can bring the same this identity information, that means the same input information to this state, so that the next state can proceed, next state and the states after that can proceed without having an issue, right? So if there were some problems with this section, making the values to 0, then this ResNet residual connection can bring the input information, uh, replacing these 0 values and continue the rest of the neural network, rest of the depth, and that is the value of this residual connection. Right? So what we do is we add this input value, bypassing this same output, bypassing this block, right? And for the this is the output of this block, and this output is added with the input directly and then normalize. So this normalization is somewhat different from the normalization that we have learned. So we have learned about batch normalization, but here what we are doing is known as layer normalization, right? So that is not that much different. So we'll explain a little about that as well, right? So then what happens is that we move into the next phase, which is known as the feed-forward neural network. So we know about it, right? So we don't have to explain that much. So this is a fully connected network, right? Uh, so when this information, when this in this section, what really happens is the self-attention, a process known as self-attention, where only the most information, most relevant features are detected based on the attention with the matrix like this, right? Where each of the inputs are mapped against each of them, and these values are mapped, and these values are added and normalized and given to this feed-forward network, where uh, all the connections of this output are processed and do the needful and give the output, right? So again, uh, if something nasty happens inside the feed-forward network, that can be avoided using this residual connection, right? And then we add this input value, and then we normalize with the layer normalization. So this is actually known as a single encoder block. From here to here is known as a single encoder block. In a encoder, there can be multiple encoder blocks. In this paper, they have mentioned like 6 units of encoders, one after the other, are used. Like say this is if this block is known as NX, there can be multiple. So we give this inputs, input encoding and this addition. This is that information. There are several encoders like six encoders, and then we get the output, right? So there are 6 encoders, right? And then we give the output, and this output is given to the decoder section, right? In here, what we do is here also we can what we are doing is we are going to give the input, but this is given as output, because what we are trying to do here is we are giving the output that was generated previously, right? So if this is the starting point, we are starting with the symbol known as SOS. It's known as the start of the sentence. So this is a specialized token that we add to this vocabulary. Like not only these normal English terms, we have some specialized tokens like SOS, which is the start of the sentence or something, start of the encoding or whatever, right? And also we have another token known as EOS. So the finally what we get is the token known as EOS, end of a sentence, which is something similar to the uh, full stop, but full stop is not the end of the sentence, right? So full stop sentence ends after the full stop, right? So it can be a question mark or something, and EOS is another specialized token uh, in the vocabulary when we are using these encoders and decoders, right? There are some other tokens known as unknown tokens. That means when we have some tokens that are not in the vocabulary, which are known as out of the vocabulary terms. So all these terms are replaced by this unknown token, right? So this is uh, about the vocabulary, right? So here what we do is for each of these for each of the outputs that we have received up to now, say like say at the first we give the in the there are no outputs, we just give the input SOS, start of the sentence, and then we process and then we get the output which is consists of one output like mama, and the second output would be SOS mama, right? So then the third output would be SOS mama asai, and fourth one is SOS mama asai pusonta, and the fifth one is the mama asai pusonta EOS, end of the sentence. Then after the end of the sentence, there would be no processing happens because this is the end of the sentence. It will get stopped. So actually, you don't have to do these things in sequential manner. Uh, Unlike in these models, like these RNN models, in these models, when you are training, you can give all of these output, all of these training examples like SOS and space, right? SOS mama and space, SOS mama RSI and space, and so on. We can give the outputs as a set of vectors, right? So what we have to do is we have to complete the what we are supposed to do is to complete the next token. So for all the steps we are giving them as a matrix. So we will discuss later how it happens. And that is also encoded with the output embedding, which is also similar to the word embeddings, word piece embeddings that are used in this section, right? And then these embeddings are encoded with the positional encoding, which are encoded in this position numbers like first token, second token, and third token, and so on. And they are given to this another masked multi-head attention, right? So this is somewhat different from the multi-head attention, but they also contain this key value and query parameters, and there's a residual connection as well. And we add the normalize, and then we give it as the only as the query value to this next step, right? So in this case, all the key and value and query are the same. So which is same as this input. In here also, the key, all key and value and query are the same, which is this input. But here, once we add and normalize with this residual information, only the query value will be set as this output, right? The key value and the value would be given from the output of the encoder. So we said that we can have like 6 or many many number of encoders, say like 6 encoders in this paper. So it can be different. So you can change it. So what is given given as the output from these encoders are the keys and values. And these values are then given again to the multi-head attention and then normalized, added, then normalized, and then again given to the feed forward network and added, then normalized. And actually, there are many decoders as well, not 6 that, but in a different number, right? After several decoders, then we move to this linear layer, which is mapping this output embeddings to the vocabulary terms, right? So because this is a softmax layer, which is uh, mapping these output vectors to the word embeddings, right? So I mean, mama may have a mama as I put all these 3 words would have some word embeddings in the singular language, right? So these word embeddings are mapped with the softmax classifier. So before that, we have to map this word embeddings to this this encoding to the word embeddings. So the dimensionality may be different. So this linear layer is used to match these dimensionalities. Right. So that is what is done with the linear layer. And after the softmax layer, uh, these these tokens, the singular tokens are generated. Right. So that is what really happens in this transformer architecture. Actually, I have explained a bit, but I will try to explain again piece by piece in the upcoming slides. So before that, as we have learned, we can have 2 different main sections, components in the transformer architecture, which is encoder and the decoder, right? But later, after going through this paper about attention is all you need, people have generated different architecture using these patterns. So for the in the original paper, it was used for natural language translation, which is translating from one language to another language, right? So you like we do it in the this is how it is done in the LSTM network, and this is how the same thing is explained how to be done with using a transformer network in this paper. But other researchers have found that we can use only the encoder and generate some specific usage out of it. Those are known as encoder only models. You have inputs, then we encode them and have the encoding, and then we have some output processing and get the output. And we have some decoder only models as well, right? That means in this architecture, we can use either the encoder separately or the decoder separately. Encoder separately is known as the encoder only models. Decoder only the separated decoders are known as decoder only models. And the encoder decoder models are the models that are similar to the models described in this paper, which is known as the encoder decoder models. Right. So let's see what are these encoder only models do. Right. These encoder models only what they do is actually they only encode the information that is given in a sequence into keys and values or into some numerical format, right? So it is all about these encoders are all about understanding the idea or the concepts in the sequence, right? Which is like the output of a bidirectional LSTM. If you think of in the sense of RNN models, right? That means we consider information in both directions, in all the directions, and see what is really inside in this information. That is the expectation of this encoder only models. So we train these models. So these transform models are trained with several steps. First, what we do is we train them with some unsupervised learning technique known as language models, where we are trying to complete certain terms, right? In in this case, how it is pre-trained is using masked language models, not the ordinary language models that we know, where we in the ordinary language models, what we do is we complete the last word, right, or the last term. But in masked language models, uh, what we do is something like this. So we have some specific, say we have a sentence like uh, I like uh, white uh, cats, or something like this, and full stop. So, so in this masked language model, what it does is they randomly select some terms, and they omit these terms and have a blank instead, and ask the uh, this neural network to predict the missing terms. So we omit this one and ask the model to predict what is there in this position, right? So that means it is something similar to what you have done in your primary education. Like you are given questions like filling the blanks, right? So in the sentence, you are asked to fill what should be there in this sentence. So there are some blanks in the sentence, and you are asked to fill them in your primary school, right? So in first year, second year, and so on, in your primary, you might have come up with this question. So that is how the masked language model is that is known as the masked language model. So that is exactly what is used to train these encoders, right? So you can train the encoder with this kind of with this masked language, and then so once the transform model is trying, these encoders are trying to learn, they will learn how the language is constructed. So what is there that is known as the bidirectional context, right? So what it is learn is known as the uh, bidirectional context. That means now it tries to understand uh, if it is I and if it is white cats, there should be uh, something like about relevant to like or preference or something, right? So that means you when you see the words around them, you know what should be there in this what we are talking about, right? So that is the idea of bidirectional context. That means in this direction and this direction, we try to understand, we get some sense or intuition, not I, but the ML model encoder under try to understand this context, and it can have will have some intuition, right? So what should be the word that should come into this place? That is what is learned in this encoder model. So these encoders are generally used for sentence classification, sentiment analysis, and things like named entity recognition in NLP, natural language processing, right? So why sentiment analysis is used? Because these encoders can have the feeling or the intuition of the sentence or the text. Then because of that, excuse me, these models can understand the sentiment of a sentence because it has the bidirectional context or the meaning or sense of a text or a sentence, right? So these encoders are used in these kind of requirements. So some of the examples are Bert and Roberta, which are open source models that are available that you can use. So these encoder models are also known as auto-encoding models. So auto-encoding means they can automatically encode the understanding or the meaning of a text or a sequence of events, right? So although actually remember, although we are explaining this with these words, right, with English or something, there you can think about these transformers or whatever, sequence models or whatever, as a sequence of events, right? So these words are just some examples that we are using, because these are this natural language processing is the most widely used application. So these are, you should think these as independent events that are happening one after the other, not independent, uh, distinct events, right? So these are like a sequence of events. So these transform models, sequence models, LSTM models, those can process these sequences, right? That is the generic idea, right? But because we are not using those things for many other applications, at least now, so we are mainly using these transformers and all those things for text processing, because that's why we are explaining it these sentences, right? So keep in mind, so those are they these are like the events in a sequence, right? So what these encoders do is they can understand the meaning or the sense of a sentence, so that they can do sentiment analysis and all those things, something like this. That is why they are known as auto encoding models. So they are encoding the sense in the uh, into a vector or into keys and values. So in here we say this is the encoded vector, right? So in here also, this is the encoded keys and values that are generated as the output of this encoder, right? And the decoder, what they do is uh, they can get these keys and values, and these as the query value, it can get these previous outputs, and then use the multi-head attention and uh, generate the next token, next term, right? Next event in a sequence. So those are known as auto-regressive models, right? Decoder models are like also known as full language models. Full language models means we know about them. When you have a set of terms, we can predict the next token or the next word in a sentence. Those are known as autoregressive models. So decoder models are like that. So in order to train the decoder models, we are using these causal language models, which are also the full language models, right? So that is how these decoders are trained. So in decoders, what they do is they predict the last token in a sequence. So to predict the original sequence, that means we remove the last sentence, last token, last word, and then or the next word. So it's about predicting the next word or the next token in a sequence. Unlike the encoder models, where it has a bidirectional context, these decoder only models or autoregressive models are unidirectional. It learns unidirectional context. That means they learn about the dependencies in a single direction. We have these sequence models like RNNs. It is analogous to these kind of RNNs, right? So they have a unidirectional context. That means it is good for modeling some time series information, right? So when it comes to encoders, those encoders can be used to encode things like language, DNA sequences, or something, a set of events that has not related to time, right? That means when you can see both directions, when it can learn the what should be there in the middle. But in decoder models, we know about the history. What we are trying to predict is the final output, right? So it can keep the historical information. So it can only keep the historical information. It doesn't know what happens after this particular time step. So this is a unidirectional context. That is what it learns. So these decoders are used for text generation, or like in the chat GPT, right? Actually, chat GPT is a GPT model, right? So now you know how the chat GPT is model. Chat GPT is a decoder only, or the autoregressive model, right? So it is a GPT model. It's an open source model where you can use it. So actually chat GPT was developed using this GPT model. There's another model, open source model was Bloom, and there are several other many other models that are using the decoder only architecture. So in ChatGPT, you can see these tokens are generated one by one. So that is how they are generated. So they are using this kind of autoregressive learning, and they can generate next token and next token one by one. So this is what really happens in the decoder only models. And in the original transform architecture, they have explained about this encoder decoder architecture, where both encoders and decoders are there. Now because there are inputs and outputs, which is a sequence to sequence model. It can also be known as sequence to sequence model, because there are input sequences and output sequences, right? In this case, so this is an input sequence. I like cats. This is the output sequence, right? Right. So, so this is a sequence to sequence model. They have used both encoders and decoders, and how they are trained, how they are pre-trained is kind of dependent, right? So there's no certain way that these how these encoders and decoders are trained. One of the common well-known open source model encoder, so encoder decoder model is known as T5 model. In this T5 model, how it happens is in encoder, some random tokens of the input are masked with unique placeholder token. That means in the certain tokens are masked. It's known as mask, but they are replaced with some special token, right? So earlier we have learned about this SOS token, EOS token, unknown token, and there's another token that we have to introduce in this encoder decode model known as sentinel token, right? So in some tokens are replaced by the sentinel token, and trying to predict what was there. So that this is known as the process of span corruption, right? And the decoder tries to predict the next token of the original sequence of tokens, uh, which is by replacing these sentinel tokens, right? So this is known as this is the work of auto regression, right? So these encoder decoder models are used for stuff like sequence to sequence modeling stuff, some things like translation, where one language is sequence of words and the other language is also a sequence of words. And summarization, where input is a sequence of text which is large, and the output is also a sequence of words which is a small sequence, right? Question answering, which is where the input is also a question which is a sequence of words, and the output is which is the answer is also a sequence, right? So T5 and BART are some of the open source examples for this model, right? So now let's try to go through each of these terms, although we have gone through the uh, content. Let's move through this through each of this content. right? Each of this component. First, look at this one, right? Where the inputs are given and the input is embed. Input is encoded with this word embedding, right? So we generate some embedding in this transformers. We propose this, not the or classical word embeddings like word to glove, but word piece embedding and some other similar uh, types of encodings, embeddings, which can be generated, uh, which is common for most of the tokens. Like the problem was that when it comes to embeddings like word to there can be a lot of out of vocabulary terms. But when it comes to this word piece embedding, because words are broken into smaller pieces of certain, which is a sequence of some characters, uh, most of the terms can be mapped into the even the unknown words or the out of vocabulary terms can be mapped with the word piece embedding, so they can be encoded easily, right? Without much unknown tokens, right? So this is an example. So if this is the original sequence, your cat is a lovely cat, right? So and there are so in your list you can have IDs like 105, and so these are the positions of your word in this list, right? In the embedding, and in that index or this ID, you can get the word embedding, which is a vector for this for each of your word, right? For word your, this is the word embedding, which is of the size of 512. It can be any number, right? So it can be 512, 1024 or something. So for the word cat, this is the index and this is the ID, and this is the word embedding. So it is a 512 dimensional vector. For each of the terms, it is the same, right? We get a set of vectors for each of the words, which is the embedding. And then what we do is we encode the positional encoding. We add the positional encoding to the word embedding, right? So, so what is a positional encoding? Positional encoding is, as I said, it is about keeping the position, which is this is the first one, this is the second one, this is the third one, and so on, right? So these are the positions. So whatever the sentence it is, it may be your cat is, or it may be I love you. In whatever the sentence it is, if the position is one, the embedding or the positional embedding would be the same, right? So you don't, for each of the sentence, for each of the set of sequences of words, you don't have to calculate the positional encoding again and again. So once you have calculated the positional encoding for the for the first position, second positions, third position, and so on, you can reuse all these positional encodings for to be added to the input sequence, right? So this is how you calculate the positional encoding, right? Uh, all these odd numbers of the position encoding is represented by this red arrow. So they are generated. They are these positional encodings are generated by this equation, this formula, where sin position encoding divided by 10,000 to the power 2 times I index, which is this index, right? This is I think 0, 3, this 1, 3, and something like that, right? Just you can go through and see if you are interested how they are actually calculated, right? So, and for the even numbers, this is the formula we are using, right? It's a cosine value. The position divided by the 10,000 to the power 2 times index divided by the D model. D model means the dimensionality of the model, right? It is 512 in this case, right? So with this sign and cost values, you can create the odd and even positional encodings, positional values for each of these sentences. So once you have created the this positional encoding for one sentence, that can be used for all the other sentences as well. So once you have calculated your cat is something, then that can be that is same for the sentence two, which is I love you, right? So it is the same. So this is how you calculated it. So you give the position and the 2 times index, and in here we use the position and 2 times I times 1, 2 times index plus 1, and give this into the formula, and you can get the values, right? So we are not going to discuss in deep how these values are uh, representing this encoding, right? So if you are interested, then you can look further how these positional encodings are working, right? So actually, still you will not get the exact idea. You will get some intuition how these are working, right? So because this was developed in 2017, actually these neural networks, how they are working, we don't really know. We only have some intuition how they are working, right? Because these transformers are working really well in the real world situations. They are used in they are used today, but uh, we can't most people actually don't exactly know how they are really working, how they are really functioning. That means why they are so much successful, we don't really know. But once you get your understanding improved, you will get some better understanding why they are working really well, more than the earlier models like RNN models and convolutional models, right? So, so you can start from here, right? So that's the idea of this lesson. So here what we do is first we get the inputs as tokens, and we calculate the embeddings, and then we add the positional encoding to the word embedding. So here what we are doing is the same. We get these tokens, and then we get the embeddings, right? And then we calculate the positional encodings only once, right? And then we add this one to this one, and then we get the encoder input, right? So that means this value is added to this value and get this output value. This value is added to this value and get this value. This value is added to this value and get this value, right? Similarly, for each of the words, we can get the embeddings, and then we add the positional embedding, and then we can get the encoder input. Right? Encoder input means input to the encoder component. You can calculate it something like this. Get the embedding, calculate the embedding, and then position embedding is there. Once you have calculated, you can reuse it for all the sentences that can be added, and then you get the encoder embedding. So now remember that the embedding size is, if it is 512, the positional embedding should also be 512, and the encoder input should also be 512 in size, right? So otherwise you can't add two vectors. Right? So now this is the most important thing in the heart of the transformer model, which is the multi-head attention. Right? In multi-head attention, what really happens is uh, something with something like having the self attention for multiple filters kind of thing, right? So in the convolutional neural networks, we can increase the number of parameters by increasing the number of filters, right? Similarly, in transformers, you can increase the number of parameters by increasing the number of heads, right? So before we talk about the multi-head attention, just first uh, discuss about how the single head attention is working, right? Or simply the attention, right? So attention means single head attention. So what we do is, so now we are considering this one. So as I mentioned earlier, over time the first one is the key, second value is the value, third input is known as the query parameter. So what happens is uh, for the this attention, so this is the multi-head attention. So for the single attention, it is the same. We need all these three terms: query, key, and value. And its attention value or the output is calculated with this formula. Right? So once you understand this formula, you will understand a considerable amount in the about the transformers. Not that much, but you will have some intuition why it is working, right? So in this case, because the same input is used as key, value, and query, for the encoder, q is equal to k, k q is equal to k is equals to v is equals to x. X means this input, right? So if this is x, this is how it should be, right? For the encoder. So what really happens is in self attention, these inputs are uh, found in this self attention matrix. How each of the input the token or the word is uh, relevant to each of the other token in the same sequence. So that is the self attention. So let's see what really the self attention is, right? Suppose this is the sentence. The animal didn't cross the street because it was too tired. So now you can see this is these are the tokens that are created for this sentence. Yeah, now you can see this didn't is not a single term. In didn't was taken as a single token. Apostrophe is taken as a single token, and the T is taken as another token. So that is how this is the functionality of word piece embedding, right? So these are taken as two different tokens. In tired also, TIRE is taken as a single token and D is taken as another token. So that is how it was might have automatically generated. These two are taken as two different word pieces, but all the other words are taken as generally single words, right? In this case. So here what we do is we are calculating the weight for each of the terms. So these are the same terms. These are the same terms that are given in these terms, right? So the animal didn't cross the street because it was too tired. So it's same as this one. For each of this output, so suppose you are taking term it is compared against all the words in the same sequence. So this attention, self-attention weights will learn that it is mostly relevant to the word the animal. It didn't cross the street because it was too tired. So what really means by it? Because it was too tired. What is it? It is the animal, right? So animal which didn't cross the street, right? That is the sense, right? So the self-attention, what it does is it learns that when it comes to it is it should be given to the higher attention to the terms the and animal, right? So when you get a sequence like this, the self-attention will map that this term, this word piece is having the higher attention to these two terms. So that is the idea of mainly one of the maybe the animal, right? So this should be the token that should be having the highest attention. So when you say it is giving the attention to the animal. And not only for it, but for all the tokens, all the words in this sequence, the attention for each of these terms is measured, is calculated using this self-attention mechanism. Right? So how the self-attention is calculated? Right? So you can think it in intuitive way like this, right? So for that, you have to look at this Q KT divided by dk times, and we take the softmax of that, and then we multiply it by V. Right? So in this slide, I have explained why we are using, but looking at this one, I can explain, right? So, so what is this? This is like the query, right? So in data retrieval, like information retrieval, a query is a term that is used for querying some data from a data store, right? So the query is something like a statement which is querying data from a data store. So this, it is like the question, right? And this K is this should be the capital K actually, right? This K is the key. So suppose we are having some query into a data store where the data store consists of keys and values, right? So the keys are small and they, so general, right? So in practical case, but in transformers, the keys and values, there's no something like that, right? So in general way, if you are querying data from a key from a data store, so you have a query. What we do is we try to match the similarity between query and the key, right? And we go through all these keys and find which key, for which key the query is mostly the same, right? If you found that for this particular key, there's a very high similarity between the query and the key, so we select this key, and then we can multiply its. So now we know this is the key that should be given the attention, and then we multiply it with this value, with this attention, with this value. So this is what really happens in this attention layer as well, where we take the multiply this query uh, with the transpose of the k vector or the k matrix, right? In whatever the way you think, right? So in simply say like q is a vector and k is a so vector, right? So we take the transpose and then we multiply, which is similar to taking the dot product of k and t, right? So when you take the dot product, if these two vectors are the same, it would be having a higher value, right? So this is the same case where when the query and the key are the same, this combination QKT would be having a higher value, and it should be divided by the square root of dimensionality of K, right? It should be capital K as well. So what is the dimensionality of K? It is the number of elements in this uh, data store, right? Similarly, uh, this is the dimensionality of K, and we take the square root of this dimensionality of K, and why we divide it? So that is to normalize this value, right? So because we can have different sizes for queries, and so we can have stores for different sizes for queries and keys, not for queries and keys, but those two should be having the same size, but their size may be different from case to case, right? But in order to normalize these values, we can divide by the square root of the dimensionality of k. If say if there are 100 1 to 100, this is the 100. Say there are 100 terms. Square root of 100 is 10, right? So then QKT should be divided by 10. That means the similarity is divided by the dimensionality of this vector with the number of dimensionality of this k vector or the v vector, right? And that value is used for the softmax. So why we are using softmax? In the intuitive sense, we are using the softmax instead of max, right? So in your mathematics, what you do is generally we take the maximum value, right? But when it comes to machine learning, we can't have the maximum value because it is not differentiable. You can't train a maximum value, right? Because it's a step function, right? Something like this. Because of that, we use the softmax, which is a bit softer, smoother version of maximum, right? That is the sense of using the softmax. So for each of the key values, we we take the dot product of say like we take the multiplication of q and kt, just like taking the dot product of query with the key and normalize it for all the key values, and then we take the maximum value. So here we don't take the maximum value, we take the softmax value, right? And then we get this maximum value, which is, and that value is multiplied by this value. This value, uh, this value in the value column, right? That is how we get the number for the single head attention, right? That means if you get some query vector, and then what we do is, so you get a query vector like here, and then for all the key values of the matrix, we find which one is most closer, and then get the attention using the maximum value or the soft version of maximum value, which is the softmax, and then multiply it with the value. That is the attention for that particular query in the key value store, right? So that is what really happens in the single head attention. So that is what we have explained here, right? So this is a calculation like this. So we take the softmax of q multiplied by kt divided by square root of 512. So qkt multiplied and divided by the dimensionality of k, which is 512, right? Which should result this matrix, right? And this same matrix, this is the same matrix, right? And multiplied by the V matrix, and then you get the attention matrix. So once you calculate the Q and KT and divide by the square root of 512, you get values and take the softmax value for each of your terms for these are the words, right? Your cat is a lovely cat. Your cat is a lovely cat. So you are taking the attention with your sentence for all the words against itself, right? So you get some values, and if you look at the addition of these values of these cells, you can say it is equal to 1, right? From here also you can get the addition would be 1 because it is a softmax. The softmax, the addition of these vectors would be 1, right? And this is later multiplied with the V matrix, and then we get the attention matrix, right? It's an example. And then what happens is that so that what we have discussed up to now is about multi-head is single head attention. So in the multi-head case, what we do is we uh, should have multiple heads. Multiple head means if this is the uh, attention, this is the attention function that we used here, right? So this is the attention function that we learned just now. And for a certain head, so if we have, when we like the multiple filters, when you want to have multiple heads, this is how you have a head, right? Each of the head, this is the formula that we calculated. That means for each of the head, we should have individual weight matrices for query, key, and value. Right? That means for the header I, that means for head I, you should have a weight matrix, a dedicated weight matrix for Q, WIQ, for dedicated matrix for W for K, WIK, for dedicated weight matrix for V, which is WIV. Means for each of the heads, for each of these query and key and value, there are weight matrices. So weight matrices are parameters, right? That we are going to learn. So in order to change the number of parameters, you can change the number of heads in your multi-head attention, right? So what it does is, so they are weighting these instead of using the query key and value directly, they are multiplied with these weight values. Q is multiplied by this weight matrix, K is multiplied by this weight matrix, and the V is multiplied by this weight matrix to get the multi-head attention. So there would be multiple these attention calculations happening, so which can be processed in parallel, right? So that is the advantage compared to the earlier RNN-like models, where we can calculate the attentions in parallel, right? So for likewise, you can calculate the headers for each of these for each of the I values, and then you can concatenate these heads, right? And you should have another weight matrix known as W output, WO. And once you multiply it all, so once you concatenate all those things, concatenate all these heads, and then multiply it with this learned W output matrix, you can get the multi-head attention, right? So this is the output of this you get from here, right? This is the arrow, right? So this is the multi-head attention of these inputs. From these inputs, you calculate, that means similar. So this is the formula for the single head. We calculate it multiple times in parallel for different K, V, and Q values, right? And that is how we calculate the, and when we concatenate them and multiply with the, first we concatenate these heads and then multiply it with the another weight matrix, and that is the multi-head attention. So this multi-head attention is later added with this residual connection inputs, and then layer normalized. Layer normalized is something similar to the batch normalization, but it's not the batch normalization. We are normalizing on the data in the mini batch, right? So mini batch or the batch, right? That means in the batch normalization, what we do is we take the values for the, we normalize for the data set in the whole batch, right? Or the whole mini batch. But in the layer normalization, we take the values in this layer, right? And those values in this layer are used for normalization, right? So it is a somewhat similar but different way to normalize the values in values in this layer. So the vector values in this layer instead of the data in the batch, right? And then we move to the and then we know that we know what is a feed-forward network and do the residual network add norm and so on. And then you repeat this encoder several times, like 6 times or something, and then we move into the decoder, right? And decoder, then we have the key and value that we receive from the encoder, and query is generated from the output that was generated, right? So that is the difference between the earlier multi-detention and this multi-detention. But in this multi-detention, this is not a self-attention because you are using a different query value. It is known as the cross attention, right? We are taking the attention with the keys and values with the queue, not with itself, right? So it's not the self-attention, but the cross attention. So when you are taking the attention, multi-head attention, uh, in the decoder, right? In this decoder, we should for each of the term. So because this is a decoder, what we are doing is auto regression, right? Auto regression means we are not giving the values after that. For example, if the word is your, all the other values should be empty, right? It is your cat. These two values should be there, but all these values should be empty. Your cat is, these values should be there, but these values should be empty. For that, what we do is we replace these values with minus infinite before we apply the softmax layer. So the when you apply softmax layer for the minus infinity, it would be 0, right? And that is how we calculate the that is something what we do before we apply the softmax value for the decoder before we because we should not have the later values in this matrix because this is a auto regression model. We should only see the things that has happened up to now in the history, but not the later events, right? So this is the block diagram. So we have this SOS token and EOS token. So say this example, like I love you very much, and we want to translate it to Italian. So it should be created like SOS, start of the Ti amo molto, right? So we take the input and then we encode it and get the encoder output. So this encoder would contain the several encoder modules that which we have learned up to now, right? So there would be certain these NX modules. There would be certain 6 or something number of NX modules in this encoder, and then we get the encoder output, which consists of key and the value, and it is passed to the decoder, where it is added as the key, as the key and the value, and this is used as the this is processed and it is added as a query. Query is generated and the key, query, value, and all these things are used in this decoder. And the decoder is also repeated several times, like the encoder. And the decoder generated some output, and this linear layout match the dimensionality from the output of this decoder to the vocabulary word embedding, and this vocabulary size would be matched with with the D model, and this vocabulary size is when you get the vocabulary size vector that is used to uh, select the most related word using the softmax layer, and the words are generated. So unlike this sequence models that we have learned with this RNNs and LSTMs, we don't have to give the inputs one by one to generate each of the terms individually, right? So in this case, for this sentence, we give this as a single matrix. So in each time step, you can learn all these values, all these empty values at the same time, right? That is the value of this advantage of using these transformers. another advantage, right? So that means you don't have to in when it comes to a system like LSTMs, you have to turn first this one your, and then you get the your cat, and that is given as the input, and your cat is given as the input, and so on. But in transformers, you don't have. You just give all these terms as a matrix, and then we uh, can train at once in a one time step. So that is the advantage of using the transform, right? In transformers, this if you talk about the loss, the cross entropy loss is used, right? Just for knowing. And but when you are making inferences, transformers make inference tokens one by one, right? So although it can learn a sentence at the same time, because we have the next tokens, all the tokens in this uh, sentence to be translated. But when it comes to generation, we don't know the later tokens that will be generated, right? So we only know the next token that has to be generated. So we have to generate token by token, which is a which cannot be done in parallel. So when you are making inferences or making predictions for the next token, you have to do one by one, unlike the training of a transform. But still, when it comes to transformers, the advantage is the training, right? So the training time is very high when it comes to machine learning. That is a significant problem, but that can be avoided with transformers, right? Okay, so that's all for the today's lesson. So if you have any questions, you can ask.